This is our last video where we're going to start taking a look at these sorts of differential equations and algorithms to be able to approximate solutions to differential equations. And we're going to take a look at this Runge-Kutta method. And there's lots of different Runge-Kutta methods, but this is one of the more popular, the fourth order type. And essentially what we're going to do is, surprise, we're going to go back to our friend the Taylor polynomial. We're going to expand it, and we're going to get a fourth degree polynomial to be able to approximate the next x, all right, or the next y, excuse me. And so we're just going to go ahead and we're going to plug all these in. And our job is to be able to solve this sort of system that's going on. All right, so we just go through, use our Taylor expansion. We get this sort of system, and we can go through. And unfortunately, because it yields more unknowns than equations, for those of you that have taken linear algebra, you know that you have to parameterize it, and that's what happens. Now, somebody went through, they figured out what the best constants are going to be, or the coefficients, and this is the algorithm that we get. All right, so this is going to be our next y value, and these are going to be each of the coefficients to be able to get to the next y the most efficiently. All right, so let's just keep this in mind. All right, and what we're going to do is we're going to go ahead and surprise, just like the last two examples, using the Euler and improved Euler's method. We're just going to go ahead and we're going to utilize our differential equation and our process to be able to approximate the solution at y at 5. All right, so let's get to it. First things first, we're going to do the exact same thing as we did before. So here is our regular Euler's method. This is our improved Euler's method. So let's just cut and paste everything. And now we're going to get our Runge-Kutta method, right? We're redefining everything. And the only thing that's going to be different is right here with the next y. All right, now we are going to have to do a number of things to get to next y. All right, so first thing we're going to do is we go back to our formula. And our formula says that we have to first get this K1. So let's not even worry about this yet. All right, that's going to be the last thing we do. But K1 is basically going to be the step size times the original function. All right, so that's not too bad. So I'm going to say K1 is going to be equal to H times, and remember the original function is 4 times x1 minus 2 times the current y. All right, so that's easy. K2. All right, so let's look at our function for K2. And it's going to be the step size times the function at x plus a half h, y plus a half k1. All right, so we're just going to go ahead and program for K2. So that's going to be h times 4 times x1 plus 1/2 of h. All right, so we just have to be careful with that. Minus 2 times our current y. All right, so now what we're doing is we're substituting in for the y, and we go back to our formula, and it says current y plus a half of k1. So that's going to be curry plus 1/2 times k1. All right, so that's taken care of for K2. Now K3, let's see, I need another parenthesis in here to take care of the H. Right? K3, the good news with K3 is identical to K2, except we're switching K1 or K2 for K1. All right, so we're just going to copy K2's code. All right, and we're just going to change that to K3, and we're just going to change this to K2. All right, so that's easy. And then finally, K4. K4 is not too bad. K4 is going to be step size of f xn plus h. So that's going to be our next x, and then yn plus K3. All right, so that's not too bad. So we're going to go back, and we are going to say h times 4 times our x1 plus h minus 2 times our current y plus K3. All right, so it closes that one, that closes that parenthesis, and we should be good. All right. So last thing we have to do, We're going to go back and we are going to program this. All right, so we have our previous y or our current y plus 1/6 k1, 2k2, 2k3, k4. All right, so we're going to have our next y is going to be equal to our current y plus 1/6 times k1 plus 2k2 plus 2k3 plus k4. All right, so all of that. Now let's see if this makes any sense whatsoever. All right, so we're going to run it and we're going to get all three of the outputs for the three different algorithms. All right, so here's our first algorithm, 11%. Here's our second algorithm, about 1%, and our third algorithm is extremely accurate. All right, so this gives us 0.002%. All right, so this just illustrates that even though the Runge-Kutta method is a little bit more taxing to program, it certainly yields high benefits. In fact, to me, and this is just my personal opinion, I actually like the Runge-Kutta method a little bit better, not just for the accuracy, but because it breaks up these coefficients into segments, as opposed to the improved Euler's method, where it's just all one shot. And of course, we could break it up. This reoccurring sort of structure occurs a couple times, so we could redefine this and maybe make it a little bit easier for ourselves. But again, just to me, since the K's are a little bit shorter to try to work with, the Runge-Kutta method is to me a little bit more preferred. And again, because the accuracy is so much better. All right, so that takes care of all of our algorithms for our solutions or approximations for differential equations. So hopefully this shows you not necessarily what a differential equation is, nor how to solve a differential equation, but maybe how to go through and utilize technology to be able to approximate the solutions to differential equations. And then when you actually take your differential equations course, not only will you go back through this in more detail, but you'll also learn the analytic methods to do this and what goes on behind those analytic methods. So that way you can get a full understanding of how to go through and solve these differential equations, and if it makes any sense, both geometrically as well as analytically.